In today's lecture, we see how the HR diagram leads to great insights about how stars are born, live, and finish up their lives. Near the end of their lives, stars also give rise to new star formation. Incidentally, we learned tons of things about material and experiments here on Earth as a result. We learn about no less than the nature of the periodic table of chemical elements, the nature of nuclear forces, and the structure of atoms. All of this from those meticulous observations by the Harvard calculator ladies that led to the organization scheme by Hertzsprung and Russell, and the grand synthesis by Bethe, Weizsäcker, and Gamow that explained how the sun works, and we'll find out explain a lot about how the HR diagram works as well. Also at the end, there's a little bit of the contributions of people like Weinberg, Salam, and Glashow that won the Nobel Prize in explaining the weak force and how it may be related to other forces. As you can see, the scientific understanding emerged after meticulous preparation, and it kind of reminds me very much of the observations of Tycho Brahe, the organization by Kepler, and the grand synthesis by Newton. For those of you that have heard about paradigm shifts and Thomas Kuhn, I would say that this is a very great example of that. In present day, we don't exactly follow Thomas Kuhn's general ideas, but we still think that the way science works requires all of those three stages. Let's look a little bit closer at the HR diagram that I introduced in the previous lecture. As you may recall, the Harvard calculator ladies created this elaborate absorption spectroscopy scheme, "Oh, be a fine girl, kiss me." It then turned out that this corresponded to surface temperatures of these stars and to their overall color and the black body spectrum. In Lab 3, you are asked to describe the color of some stars. That is, of course, because the red stars have lower surface temperature and the bluer stars have higher temperature. Two of the stars that I ask you to observe are tinted in those two colors. Now those stars in the HR diagram were all at known distances. To compare them, Hertzsprung and Russell placed them all at 10 parsec or 32 light years away. If you place the sun at 32 parsec away, it would be basically one of the relatively dim stars in the sky. Its luminosity would be 10 times brighter still than red dwarf stars at the lower bottom part of the diagram, and 10,000 times less than the supergiant red orbital that are at the top of the HR diagram. In this week's lab, the stars that you're going to observe are very much brighter than the rest, and yet they are red. What is your conclusion from this information? Again, two of the stars that you're going to observe in this week's lab are red, and yet they're very, very luminous. What is your conclusion? Indeed, they are not on the main sequence. They do not burn hydrogen into helium in their core. Rather, they're giants or supergiants. Try to answer the following question. I'm going to let you read and come up with the answer. Okay, you should have found out that the correct answer is B. Antares is actually a red supergiant. It is not a main sequence star. Every square inch of its surface gives off much less light than every square inch of the solar surface, of the sun's surface, but it is huge. It has a huge surface area, larger than a sphere that would encapsulate not only Earth but the orbit of Jupiter around the sun. Here is another question that relates to the HR diagram. All stars on the main sequence do what? In this slide you have first of all two links. The first is to a short movie describing the formation of stars, and that is an animation. The second movie then describes a region where stars are actually forming in the Orion Nebula in the constellation Orion. You will notice that the collapse of very sparse interstellar clouds of matter into a star requires a slight increase in density. That density overcomes the tendency of hot gas to expand, and gravity takes over, and as a result those clumps collapse. In the HR diagram next on this slide, after you click or press the arrow, you can see that stars take a track towards the main sequence called the Hayashi track. This is named after a Japanese astronomer. The orange-red region from whence these stars come in the HR diagram are called the Hayashi belt. Those stars shine for a very short while. That actually is a result of them collapsing. But they are nor red giants, neither red dwarfs. The last picture shows a tad more informational details. But the question remains, where are those stars forming? Here is one of the regions where stars are starting to form. It is also in the Orion Nebula, as you've seen in the second link in the previous slide, but rather than being in the Orion sword region, it is in the lower left part of the Orion belt. This is a region where there is interstellar cloud that's a little overdense. Now what it means that it's a little denser than usual is that it has about 10,000 atoms of hydrogen per cubic inch. 10,000 per cubic centimeter, about 200,000 per cubic inch. Now that's nothing in comparison to the density of the sun, that has basically 1.2 10 to the 21. That's 1200, and then 1200 million trillion atoms per every cubic inch. So as you can, that's twice Avogadro's number in chemistry. So as you can see, those dense regions in between stars have way to go until they clump to the density of an actual star. Guess what? This Horsehead Nebula was identified by a lady by the name of Wilhelmina Fleming. This lady is the same lady that organized and led the Harvard calculators that cataloged all the stars that led to the HR diagram. This is a similar picture to the one that you saw more in details in the second link. Look at those bumps hanging in that veil in the Orion Nebula, in Orion's sword. Those clumps you see look like deformed tiny eggs of something, and one that's a dark disk. Each clump is actually the size of our solar system actually even larger. This is at star formation, therefore this would be the size of the largest portions of the solar system that we can barely see at present, something called the Oort cloud. This would become a shining star with its planets. So we found two regions where stars are being born, and there are lots more. I'll show you a couple more. But how do we know about the Hayashi belt and the Hayashi tracks? After all, those stars that are forming, we do not know how much energy each is giving off. What's their luminosity? The way we do is we look at regions like the Orion Nebula, and we find that there are regular stars there with the regular type of spectrum that fit nicely on the HR diagram. This is in the example in this slide where you see main sequence stars on the left, slanted, and scattered around are protostars, that is stars that are shrinking and giving off radiation, and they are together. These are usually referred to as star nurseries. Here is another star nursery. This picture is in a region called the Eagle Nebula. This picture is actually in the infrared part of the spectrum, and in it you can see through dust. In the next picture you'll see the same exact region in regular light. The middle of this picture is the big pillar on the left on the next picture. Go back and forth. This region of star formation, that's also referred to as the pillars of creation, is the same region you're seeing in the infrared picture. And it shows that in a cocoon of dust and dense gas, stars are being formed. What we see in the infrared are those stars that shine in the infrared at the very beginning of the Hayashi belt. Some stars are in the main sequence, some aren't. This is an artist rendition of the dark disk that you've seen a couple of slides ago in the Orion region. It's just a simulation. It's a simulation of how stars are being born and how a solar system is being born. It's not a picture from a telescope, and although the shape bears resemblance to the dark disk, this is just a simulation. These are helpful, but we do not consider them to be as strong an evidence as an actual observation. In any case, emerging stars shine before reaching the main sequence. Click and move to an HR diagram of the Hayashi belt objects. How do they shine? The answer: they are contracting. That's it. Yes, a clump of matter collapses as the atoms are influenced by gravity and speed up towards a smaller center, a smaller denser center. The same way a rock falling from a cliff also accelerates, speeds up, gets momentum, gets higher speed. All those atoms then collide with each other and make for very hot regions. Hot regions not only glow, but the faster the gas moves and the hotter, the higher the pressure, and that pressure stops the gas from further contracting. Still, they contract. That's because the surface radiates away some of the excess energy. As a result, there is nothing to stop them from further collapse, further go to higher temperature, until it is so hot in the middle that fusion of 4 hydrogens into a helium atom can begin. Okay then, try this one. periods here mean that the Hayashi belt and Hayashi track stars only exist for hundreds of thousands of years rather than billions of years. Sometimes millions, but still not billions of years. Of course, the correct answer is C. Back to the main sequence. And remember, all those stars have hydrogen fusing into helium, as we have shown in lectures 13 through 15. Also remember that the stars on the upper left are more massive, and we found that by observing double stars that orbit each other. As you recall, for example, orbiting the Sun, that's more massive, at the same exact distance, will be way faster than orbiting the Earth at the same distance, just because there is more gravity. Therefore, you can tell the mass from the period. So, if you have a more massive star, you basically have higher pressure to support against that mass, which means in the center the temperature is higher and the density is higher. As a result, protons collide more readily and faster with the other protons, and the rate of turning hydrogen into helium is much larger. Yep, we have E equals mc squared going bananas. Lots more energy is released, and faster. Those stars burn off faster. That's why the more massive they are, the faster they burn. The fat ones die young. Most stars in Orion are main sequence stars. Surprisingly, they are fairly bright and blue, and that's because of something we call a selection effect. Without a telescope, we see stars that are actually relatively far away because they're so much brighter. With a telescope and taking account into distance, we will have an HR diagram as in this slide. If, however, we did not know about the selection effect, the main sequence would not have an overabundance of red stars in the main sequence like we now know that there are. The star on the upper left corner of Orion looks red, like Antares. It is also a red supergiant star. Even with our best telescopes, when we look at regular stars, all we see is 1 pixel of light. Even with the best resolving telescopes, all we see is 1 pixel of light, even if the picture is 10,000 by 10,000, and we look with the best magnification, still 1 pixel. That's not true for that red giant. This red giant, by the way, is called Betelgeuse, or in the original Arabic Betelgeuse, which means the house of nuts, nuts from a tree, not the other kind. In this image we explore how red giants work. Once there is no more hydrogen in the core, the helium core is starting to collapse, the same way that new stars collapse. That's because it's radiating away its excess heat. This collapse then gives extra energy that's radiated away to the intermediate radiative zone, actually the inner radiative zone. That injection of energy starts fusion there, where usually there was not enough density and temperature to start fusion. So now we have an hydrogen burning shell around that inert helium core. Suddenly that quick production of fusion in that outer core region gives a bunch of energy to the outer regions as well. As a result, there's enough energy to puff up the star to giant proportions, and the star encapsulates all the planets without problem. Like depending on original mass, it will easily envelope Mercury and Venus our sun may even grow when it becomes a red giant and envelope Earth. There's enough fuel in this extra tank of the outer core to keep this red giant star going for an extra few millions of years. One reason we have so many giants is that every star becomes a giant, and some of them do a little more than just burn hydrogen in their outer shell. We will learn about those in the next lecture. All the while, when a red giant is shining, the helium core is continuing to collapse. Its collapse is slowed down by heat from the outside layers that are fusing. Once the outer layer fusion subsides, the core collapses faster until helium is starting to fuse into heavier elements. Why is that? Look at the periodic table again. 3 heliums, when you join them together, how much mass do you have? It is a number that is smaller than the mass of carbon. As a result, we have E equals mc squared available again in order to run that helium core. But there is a huge difference between helium fusion into carbon and hydrogen fusion into helium. We don't have to rely on the weak force at all. We don't have to transmute protons into neutrons. You may recall that only 1 in 10 million trillion of the proton-proton merging interactions resulted in a proton becoming a neutron plus anti-electron plus neutrino. The process of helium becoming carbon does not require that. As a result, it is 10 million trillion times faster. So instead of billions of years, this is now going to be a matter of minutes. This is called the helium flash. So much energy is given off that the outer layers of the red giants are blown to kingdom come, or just into empty space. The size of this outcoming stream of matter is huge. Actually, it's so huge that it can be seen as some sort of a nebula, and hence it came with that name, planetary nebula, although it has nothing to do with planets. It is going to be the fate of our own sun to become a red giant after 5 billion years from now or so, and then to become a planetary nebula where everything's hurled outside. This beautiful outflowing end to the life of those stars is called planetary nebula for a historical reason. In about the 18th century, astronomer William Herschel discovered Uranus, a planet. Then Neptune was discovered in the early 1800s. Everyone wanted to find planets and become famous. So they found those extended objects and called them suspected planets or planetary nebula. Guess what? For one thing, most of them are not on the ecliptic even, that imaginary plane where Earth and the rest of the planets orbit the Sun. So they're not planets. They're dying stars. Fast forward 200 years. A big question now was how we knew that these were post-red giant explosions, and why were these signatures so weird in shape? Why are some of them like the hourglass nebula that you're seeing? An Israeli guy that often plays chess with my 76-year-old father, yep, his name is Dr. Noam Soker, gave a neat answer about 30 years ago. He says, because these star systems had planets, that's why there is this weird shape. What? Yep. In a red giant stage, the star expanded to encapsulate the planets. In the process, it swallowed those planets, and the planets in turn churned the red giant. And as they churned the red giant, they burnt to a crisp, but they gave it extra rotational speed in its middle latitudes. As the planetary nebula happened and exploded, it could not have been symmetrical, because those middle latitudes rotational parts would go in different rates than the other parts of the sphere. The ring nebula we've seen in the previous slide is perfectly symmetrical. This one is not. We still do not exactly know why this planetary nebula in this slide looks the way it does. Looking a little closer at this picture, we may see that in the middle of the planetary nebula, amidst all the material that's held away, there is a star. Actually, you may see two stars, but one is a background star that's further away. The other is the leftover core that's made almost completely of carbon. It has no energy source anymore. It's just a rock made of a lot of carbon. It's just very hot and it shines brightly. It's not shining so incredibly brightly to outshine the rest because it's tiny. It has a mass closer to the mass of the sun, but its size is about the size of Earth. Very dense. Guess what? If it is really made completely of carbon, it's the bigger diamond out there. But don't hold your breath. Landing there would be impossible because of the incredible gravity and the incredible temperature. This white dwarf is inside the ring nebula near the star Vega. Click and see another such white dwarf near Sirius, the brightest regular star. That brightest star in the picture is actually not Sirius itself. This is a picture in the X-ray part of the spectrum. The white dwarf here shines brighter than the regular star. That's because white dwarfs are 100,000 degrees on their surface, whereas a regular star like Sirius is at least 10 times cooler. So Sirius is kind of bluish, and that's where it shines brightest, whereas Sirius B, the white dwarf right next to Sirius, shines brightest in the X-ray part of the spectrum. Let's try one more. Stars that are half as massive as our Sun are take a guess. In conclusion, the life of a star similar to our Sun on the HR diagram starts in the Hayashi belt, not in this picture. That's basically in the middle right of this picture, just above the 3000 and below the red giant. It moves towards the Sun now position, then to red giant position. In immediate steps that I didn't explain here have to do with variable stars. Then we get a planetary nebula, then we get a white dwarf. Now what happens to stars that are to the top left of our Sun is going to be described in our next lecture.